Hello and welcome to Down to Earth with Terry Virts, where we talk about what matters down here on planet Earth. If you love the podcast, please give us a rating and subscribe. And today I'm super excited to have Dr. Jim Head back for part 3 of our ongoing series on the planets. We've made it from Mercury, Venus, and Moon, and today we're going to start with Mars and see how far we go, but I have a feeling we may just get stuck at Mars, so we'll see how that goes. Dr. James Head is a professor of planetary geosciences at Brown University, and he's worked on projects ranging from training Apollo astronauts back in the day to be geologists, to robotic missions to Venus, Mars, and the outer planets. This is part 3, like I said, in our series about the planets, and so we'll see how far we get. Dr. Brown or Dr. Head? Thanks for coming back. We were laughing about that before we got on.
No
Dr.
problem.
Jim Brown from Head University.
There you go. I get mail all the time. Dr. James W., Head, Department of Geology. You know, I just forward it on. That's good.
That's all right. Well, thank you for coming back. Like I said, we got stuck at the moon. We're not able to get out of its gravity on the way to Mars. So today I'd like to talk to Mars. And, you know, of all the things that NASA's done in the last 30 or 40 years, you know, the ISS, Hubble, Mars has been at the top of what we've been doing, which is it's one of the highest priorities for sure for the agency and other countries around the world. Why do you think that is?
Well, I think the key point is that Mars is probably the most likely accessible planetary body to actually have had life, or maybe still does have life. So this is really the intriguing question, I think, for all of us is, what is the origin of life? Was the origin of life on Earth? What does that mean? When and where did it originate? How did it prosper to what we see today? And what kind of environments permit that? You know, I mean, we're going to see the Hubble Space Telescope here momentarily. Unbelievable. It's just going to revolutionize our very way in which we conceive things. Absolutely no question. But that question is going to remain, and Hubble is going to make us realize how small we are. And so Mars.
You mean James Webb?
Did I say that?
You said Hubble.
I did. I meant
the James Head Space Telescope.
Yeah, that's the one. Yeah, I'm probably the only person in the room here that actually knew James Webb, and I keep doing that. But it's an amazing, the James Webb Telescope. And what a tribute to this guy who was an early leader of NASA, who really what he was doing. Anyway, I apologize for that. But bottom line is Mars has everything. It's it's 1/2 the diameter of the Earth, but the beauty of it is that it preserves the geological record over 4.5 billion years. And so we can actually see from today with the ice caps at the poles back into time, look at the geological record to see what's changing as a function of time. And a lot changes, and we can really document that.
Right. Why does Mars preserve it and say Earth doesn't or other planets don't?
Yeah, the key is that for the last 3 billion years, Mars has been pretty much like the Antarctic dry valleys, like very cold, very dry. And so rainfall and erosion appears to be limited to the very earliest history. So that means that you don't get the kind of intense physical and chemical weathering that we see all the time. You know, we have a rainstorm here, and half the lawn gets washed down into the bottom of the driveway, and all kinds of stuff's moving very fast. And also, of course, the major issue is plate tectonics. The Earth is constantly rejuvenating itself by forcing material back down into its interior, creating new material. And what that means is that the early history, 2/3 of the history of the Earth is largely gone. And so we don't know what those formative years look like. So Mars preserved that. And it not only preserves the geological record, the climate record as well. So we can actually look at the alteration of minerals on the surface as a function of time and see what's changing. And that's I spend actually, I would say probably an hour in the middle of the night thinking about that. I get some of my best research done then, but anyway, that's another.
My most recent book, How to Astronaut, the first chapter, it was like 1 a.m. I was laying in bed. So I got my iPhone out and I just dictated by talking to Siri. And that's how I wrote the first chapter. Was at 1 a.m. I emailed myself the chapter. That's when some of the best work happens.
You should say by Terry Virts.
Excuse me.
By Terry Virts as told to Siri, you know what I mean?
Exactly, as dictated to Siri. So Mars is kind of like my garage. Never really gets cleaned up, and it's preserved the earliest geological history. Because that's interesting. The plate tectonics ruin. Well, they just disappear. History disappears forever. What's the oldest rocks that we can see on Earth
Well, we see
that hasn't been subducted?
60% of the surface of the Earth, 60% is less than 200 million years. That's less than 5% of the planet's age. So it decreases as a function of time. Continents have older rocks because that's the scum that gets preserved. But even there, you're eroding things down, you're lifting mountains up, and then you're eroding them down. And so basically, we have rocks from about 3.7 or so billion years old, but they're very minuscule. We don't, some places in Australia and cratons of the continents, but it's not a good geological record that you can really interpret. You can really unravel. Oh, what was going on here? Was this a mountain range or was it where? So those are the challenges we have, and the planets provide that perspective for us. I mean, who would have thought to go back and look for impact crater deposits? Well, there is one in Arizona, but no, they're all over the place back there. So we get informed about the early history of the Earth from Mars and from the Moon and the other Earth-like planets.
What other planets have plate tectonics? I know we talked about this before. Is Earth the only one in our solar system, or moons? Planets or moons?
And I think it would be safe to say that the Earth is the only planet we know of with the classical plate tectonics like we see them with this recycling. We had hoped that Venus, we had thought that Venus probably would, because it had this size, but that was the test. Would it have it or not? And the answer was it didn't, at least today. On the other hand, we still don't understand what's going on with Venus. It's possible it could have had an earlier phase of plate tectonics that in fact froze up, for example.
That's really interesting that the Earth would be the only one. There's so many things about Earth that are unique for life. Does that play into it? Does plate tectonics somehow make life more, or maybe not? I don't know.
Yeah, no, it's a good question. And I think a lot of people would feel that way. There's a couple of elements to that. One of them is, of course, the Earth has water. A lot of water. I mean, a lot of water, okay, to surface. And it's not a scum, it's like a lot of water. So that obviously has something to do with life. And indeed, when that material gets pushed back down into the interior, it actually carries a lot of water, wet sediment, and things like that with it, which remelts and comes back out as the volcanoes. So all the volcanoes along the west coast of the United States, Mount Shasta, Mount St. Helens, et cetera, they're all the surface result of that stuff going down and remelting and going right up along that line. No question about it. And so that adds to the atmosphere. It changes the atmosphere. It adds water, and a constant source of water into the atmosphere. So, there is a lot of thought that without that lubrication, maybe you can't have ongoing plate tectonics. Maybe that's one of the reasons Venus doesn't seem to. It's hot and dry. Maybe the water is not so easily recycled.
Well, like an engine without oil freezes up.
Bingo.
Maybe a planet without oil will freeze up too. That's interesting. I never thought of. And volcanoes are probably good for life because they shoot water, but they also bring up other minerals that we wouldn't get. They're also bad for, there's at a certain stage, it's bad for life to have too big of a volcano. That's interesting. I never thought of that relationship. So maybe that's in the negative column for Mars, since it doesn't have plate tectonics.
But it has water, no question about that. So
yeah.
One other thing about volcanoes, while you mentioned that, I think, I study volcanoes, okay? And, I'm a geologist. I want to see how things form. Actually, I'm a crime scene investigator. Typically, the crime has been done. I pick up a rock, and it's something that's happened tens to hundreds of millions of years ago. So I have to decipher that. So when an active eruption occurs, man, no problem. Nobody's flying there except geologists. Everybody else is flying the other direction, okay? And so we get to see how these things work in an active way. And it was funny when we I did a lot of work on Mount St. Helens right after the May 18th, 1980 eruption. And we wrote a short paper as part of the USGS, and it was not accepted because it was found to be too alarmist. What we said was, actually, this volcano is not a major volcano. It's actually a minor one compared to all the other eruptions. And they were, oh, we can't be saying that. I mean, I understood, they didn't want to, scare people in this context, but it's really interesting. It's like global warming, no, it's coming, it's happening, no question about it. But don't be, no, it's just not having too much of an effect, So those are the kind of things. Anyway.
That's interesting. Even with we just had a guest on talking about the Wuhan Lab leak, and the top scientists in the country didn't want to say that because it would be too alarmist. That's interesting. It's not, of anybody, scientists should be the ones to just tell it like it is. It is what it is, and not try and not scare people. But that impulse is there.
Yeah, it wasn't the scientists so much as it was the media people, the representatives, et cetera. And oh, by the way, along those lines, there's a new, I saw on NPR the other night, there's a new movie coming out on Netflix in which, I can't remember the name of it, of course, but basically it's about a comet coming in. And a lot of it is about these two scientists. It's a planet killer, okay? These two scientists who are trying to convince the media and the president. There's some hysterical outtakes in the president's office. Meryl Streep plays the president, and there's a couple of doodahs on the, the classic TV news people. No offense to them, but there's some stereotypes, just like there are with scientists. Anyway, that's an interesting one because it does explore this thing about, how do you convince people? You can't just say it because
I highly, highly, highly recommend that everybody watch. It's called Don't Look Up. Meryl Streep is incredible, like she always is. Leonardo DiCaprio and Jennifer Lawrence are the two scientists who are trying to convince everybody. And they made the movie about climate change. Like there's this climate change and a lot of people are ignoring it. But it really applies to any truth where there's a truth and lots of people tend to ignore it. And you can apply that to many issues that we're facing today. It's a great film that makes you think, like, how do you convince people that something's true? I've been thinking about this deeply, and it's a real problem. And I think it comes down to education, like at Brown University and not at Brown, I just did a speech for a group of middle schoolers. Kids need to be taught to think critically about things. And it comes down to parents, around the dinner table, mom and dad need to be going, what do you think of what's going on in Russia today with Ukraine? Or what do you think about the money versus, I don't know, whatever issues. And don't just teach your kids to believe what you believe, teach them to question things and have critical thinking. Because a lot of people don't have that. I think that's an important skill.
I just was writing a note to my friend who was bemoaning the fact that NASA wasn't paying as much attention to dust in the spacesuits as they should be. And I said, look, we have two problems today. One of them is that critical thinking and common sense are becoming extinct. And I've got this great poster that one of my students gave me. It's a picture of a superpower, super, whatever they call them. And a little bubble coming out, it says, it said, common sense, so uncommon, it must be a superpower. And coming out, it says, I feel my common sense tingling. You know what I mean?
Anyway. That's important. And that's really a scientist's job. The specific things we learn and talk about are interesting, but the most important thing about science is that ability to think critically and don't believe things based on your ideology, believe them based on your data. And if new data comes to light, you have to be able to change your opinion. I think Einstein was the most famous. He believed in the static universe idea where the universe just was. And, Edwin Hubble discovered the redshift, and he figured out that the universe was actually expanding. And if it's expanding, then it used to be, smaller. And that's where the Big Bang idea came from. And I think Einstein later in his life said that his biggest mistake was not believing's the wrong term, was not subscribing to the Big Bang idea. But that's one thing that science can teach us all, is that sometimes you need to change your belief about something because maybe you were wrong, and that's a really hard thing for humans to do, but I think it's an important thing for all of us to do.
And I think you're absolutely right. And I think the problem is that there are two things about science. One is that science is just very simply, as we've talked about before, is just the exploration of the unknown, and almost everything is not yet known. Now that doesn't put you into a very positive position when people are saying, well, you're an expert. they want the answer, and you say, well, almost everything's, well, then let's find somebody who does know. You know what I mean? Oh, that politician knows. They just speak it. And I think the other part of it is that we sadly with the with a multiverse, and I mean with the way we're acquiring data now and the way we're becoming isolated, that isolated from the point of view of the information we get, is that it's also hard because AI is such that you end up, well, you know how this works. If you search for something online, like a power mower or something, you're going to get power mower ads for the next week, a month, maybe forever. And
not only search, if you're just talking, these things are listening all the time.
That's right. And that's the problem. So the problem is you're actually getting the information that it thinks you want, and it's reinforcing this. This is why everybody is in their own little bubble. It's terrible. It's terrible.
Yeah. So there's a movie called The Social Dilemma, another one that I highly recommend. Have you seen that?
No, I have not, but it's on the list.
It's about algorithms and how they're just destroying our lives. I think Facebook found that hate is 5 times more powerful than love. Like if you hate something, you're 5 times more likely to click on it and keep on clicking on it. And clicks are the coin of the realm. That's why these companies are worth trillions of dollars. So yeah, that it's really important to understand how we're being used by computers, because are you a science fiction fan? Did you ever like Isaac Asimov?
Oh yeah.
He had his 3 rules of robotics.
Don't know them, but yeah.
It was like robots can't harm people. Robots have to follow human orders, and unless it violates rule number 1, and robots have to protect themselves unless it violates rule. Anyway, it's a really great rule that we should have for our robots, but we don't have that. And as we get this technology in terms of AI and actual physical robots, I'm afraid that we're letting them grow and develop and advance without thinking deeply about what kind of limits should we put on these robotic drones that kill people. For the last 20 years war, like how far do we want to let that go? And there's a lot of people that don't have any limits on that. So that's another thing that we need to think about, is what kind of limits are we going to put on automation?
We had an extensive discussion in class this morning about AI and just this very topic. And the definition of AI that was put forth first is to make computers think more like humans. And I said, no, well, yes, that is what people are trying to do. But what you want to do is make computers think in ways that humans can't think. That's the key. And there's this great book by Richard Hewer, who is a former CIA analyst, and he wrote this book on the art of intelligence analysis. And it's a short read, a couple hundred pages, maybe 150 pages, but he points out some really fundamental things. His logic was, how do I understand why we screw up assessments of threat assessments so often? And the answer is, he points out that is basically about the human mind. It's not about intelligence, it's about intelligence. It's about how you process data. It's about your mind. And he explains those variables and points out that we can only keep in our mind 4 or 5 things at the same time. And so our decisions are, and it's the last in, first out kind of thing too. So, it's just the way our minds work. And so that's one of the points here, is that the machines, you want that algorithm. Hate is 5 times more profitable, more common, you know what I mean? And so that you wouldn't get that from your normal assessment. But those algorithms, which is not teaching you how your brain works, but teaching them how the brain, but it's teaching them what to do that you can't do. That's the coin of the realm too. So we'll see what happens here.
Yeah, that's so interesting. And that's really, it's so powerful. Automation is so powerful in terms of physical robots and the software and algorithms, all of this technology. And it's growing in a way that's not limited at all. Like I don't think our Congress is thinking deeply about this and making smart regulations of how to handle things in international treaties. It's just happening. And so if Mark Zuckerberg wants to make something happen, he can do it pretty much without limits. And That's something that I think, and I know the big tech is trying to do the right thing, and they Google and they have to regulate themselves because our government is certainly not doing it. To say the
Well,
least.
in principle, yes, but I maybe don't call me well, I don't think of myself as a pessimist, but they speak a good game, but
Yeah,
it's the profit motive here, folks. And
yeah,
we all know how that works. And I
yeah,
don't, I'm not, Mark Zuckerberg has the daily ear of a quarter of the world's population. There are like 2.4 billion people on
yeah. On
Facebook.
Facebook.
And this is not
Well,
even, Facebook is for old people, by the way. If you
right,
haven't
exactly.
like,
Yeah. Facebook's that, like, the kids roll their eyes when they talk about Facebook. That's the grandparents are on Facebook.
yeah, exactly.
But that's in America. But in other countries like the Philippines,
Yeah.
the Philippines are going down the road of electing the children of former dictators because of the Facebook campaign that they're doing, misinformation campaigns on Facebook. Like Facebook literally overthrows countries and smaller countries in ways that we don't have here because they give free internet, and and the phones come prepackaged with Facebook, and that's how they get their internet. And so for people that are poor, that's their access. And so yeah, these questions have nothing to do with Mars, but they're really interesting things for us to talk about.
Well, they do, because if we didn't have AI, we wouldn't be able to launch these spacecraft. Think about this, okay? Basically, and land them successfully. When that spacecraft, you see the 7 minutes of terror, or I remember watching Viking 1 lander land, we were watching the descent profile, and we knew that the signals, the beeps that kept showing up during the descent were sent 15 minutes ago. And as it reached 15 minutes to the ground, it was either a pile of metal on the surface, or it had landed safely. And that's why you need autonomous things in space. I mean, good grief, of all people, this.
Right.
But when things are going on out there, you can't communicate with it. So it has to be able to recognize and solve the problem. And if it can't deal with it, then it goes into safe mode, which is the best thing to do. And so that's an example of good artificial intelligence.
Right. Some of the experiments I did on ISS were designed of how are we going to do operations when we're on Mars, where it takes minutes for signals to get back. On the moon, it's seconds, right? It's a 2.5 seconds or a couple second latency, which is annoying for a conversation, but you can have it. And unless you have to make a decision in 1 second, it's not too big of a problem. You did operations on the moon with the Apollo guys, and so was that latency a problem?
No. I mean, look. I mean, these are not motor mouths when they're on the moon. They're doing work,
right?
And so, no, it wasn't a problem at all. In fact, it bothers me when people say, "Oh, we have to have." We can't stand this latency. And I said, look, unless you're doing a far side heart transplant, I think you're not going to have a problem.
So I think it's going to be fine. But Mars is different, right? It's like you said, and because we're going around the sun, sometimes it's a lot longer when we're on opposite sides of the sun, and sometimes it's a lot shorter.
So this is one of the things I've been trying to talk to, our groups at NASA. Again, we talk all the time in terms of like how are you going to organize crew training, et cetera, and scientific interactions, et cetera. And one of the points is if we don't practice on the moon, as you well know, the astronaut has essentially the absolute best situational awareness on the surface, in this ISS surface anywhere. Right. And so you need to respect that. And the same on the surface of the moon. Our strategy for Apollo was TTT, train them, trust them, and turn them loose. And if they needed us, they knew where we were. Okay. But, it's not like, hold up this rock. Should we take this one? You don't want to do that. Oh, let's get them a little iPhone here. We can text back. No, you don't want to do that. They're on the moon. As Dave Scott would say. Dave Scott said, I think I mentioned this to you, that when he came back, we had a great conversation a day after he came back. He said, Jim, I was having so much fun doing the geology that I didn't even know I had my spacesuit on. Now, I could only say that I would be looking over my shoulder to make sure the Earth was still there. But once in a while, But that's he was in the zone. He was in the zone, and you don't mess with that with over communication. So And the other thing is that, of course, you can't do that on Mars. So you have to learn how to teach them to be on their own, to be able to have a debriefing after they get back from the EVA, practice that, because that's the way it's going to be on Mars, okay? You know what I mean? You're going to have a broad scale back and forth debriefing, which isn't going to be in real time. That can't be on the surface, yeah. Anyway, exciting stuff.
Yeah. They'll like record a message and send it back, but it won't be a conversation in a traditional sense.
Right.
So I'd like to learn about what Mars is like, maybe through the missions we've done. I mean, it's what, 3/8 the gravity, very thin carbon dioxide atmosphere, super, super, super cold for the most part, no magnetic field. So there's lots of radiation. Those are the basics, but like, can you walk us through? So you talked about Viking, it was 1976. Right. That was a lander. And then in the 90s, we had the first rover. Now we even have a helicopter. So like, what have these missions been, and what have we learned from them?
Yeah, a quick review of the geology here. So for context, basically you mentioned a very thin atmosphere. It's 6 millibars compared to the 1,000 millibars for the Earth's atmosphere.
Right.
And the temperatures are way cold. Okay, I mean just way below zero.
I'm in Iowa right now. It was minus 31 Celsius last night. It was like cold. It's the coldest I've ever been, except for the day I was at the physical South Pole. I think that's the only time in my life it's been colder. Not doing winter survival training in Russia. I've never been minus 31 C until I got to Iowa. I digress.
That's okay. This the current surface of Mars, the mean annual temperature is 213 Kelvin. So melting of water is 273. I hate to do that because but it's the way I think about things.
Yeah,
it's really cold. Okay, so
minus 60 C. Yeah,
yeah. So it's and so if you the thing of it is that it's just a frozen world now. Okay, pretty much. Okay, but back in the past. Okay, then this is the thing about the geological record. In the earliest of the 3 periods, there's a Noachian, Hesperian, and Amazonian. In the earliest, from about 3.7 billion years ago to previous time, there's a lot of evidence for rivers, okay? Literally dendritic, kind of like tree-like patterns of things running down slopes, etc. And they collect in craters and other low depressions, and they form lakes, which have a channel going in, looks like they fill up, and then a channel goes out the other side. There's hundreds of those. And then those are open basin lakes, closed basin lakes, where the water flows in. It apparently didn't fill it up enough to go out the other side. There are another couple hundred of those. So there's lots of evidence for running water. And the prevailing idea is, hey, it was warm and wet like it is today, above 0 centigrade.
Right.
And so, wow, that's cool. Okay. And so, that's the Holy Grail. Well, let's go back there and see whether there was life or not. And the problem is, the other thing is, we observe from orbit remote sensing data, which tells us there are clays on the surface. Clays are, sticky minerals that form when there's a lot of water, and preferably the water is hot. Okay, so wow, warm and wet, hot, clays, etc. And then it changes from that point on into this cold and icy climate over time. So what's the question? Well, the question is, when we do climate models, okay, there's a big factor there, which is the faint young sun. The sun has increased in its intensity with time, and that's caused the temperatures on the planets to increase as a function of time. And Mars is much farther away from the sun than the Earth is, so it's even colder. So the Earth is thought to be cold in its early period because of the faint young sun. It's about 70% of the power and the heat that it's delivering to the Earth and Mars than it was before at the beginning. So that means that it's too cold. You 226 Kelvin. You can't get temperatures above, so you have rainwater and so we see the geological evidence for all this runoff and lakes, etc., but it doesn't seem to compute. So instead, it looks like there's ice all over the place. And so the question is there a way you can melt that ice over a short period of time and produce all the features that you think are forming from a warm and wet climate? Okay, so there's two kind of parallel things. what is it? So for example, if you warm up, hey, here's a thought, let's warm up the Arctic and the Antarctic. They melt. Okay.
Right. They
So
do.
they do, yes. So
real quick, I'm sorry. So you
yeah,
said the sun used to be putting out more energy.
less,
It's cool.
less in the
Oh,
past.
so the sun is hotter now than it was a billion years ago.
That's right. That's right. So
Okay.
during this
Because
early
it's
period,
burning a different type of fusion. Okay.
it was 70% of the heat, of the luminosity, which is
Right.
translated into the heat.
Right.
Only 70%. Now it's 100%. Okay. So, that's
So
a
a
big,
cooler sun had a warmer Mars. That's the
well, that's
question. Why is that?
enigma. Yeah. And could these
Hmm.
features be formed by some other process? Okay. Like a melting of glaciers or melting of ice, et cetera, like that, by a transient event, not a long-term ambient background climate.
Ah.
So this is a big deal.
So Mars might have just warmed up, melted, made lakes and rivers, and then frozen again. That
Yeah.
might have happened.
Yeah, exactly. And that's the research that I'm working on every day. All yes.
Oh, wow. Okay.
Yeah, all day, every day.
I didn't know that was the question. Okay.
Yeah. And so this is a big deal for life, because if life, if it wasn't warm and wet, does that decrease the possibility of life? Well, to me, it doesn't, because, like you've been to Antarctica, I've spent 5 field seasons there, and
Wow.
there is life there, okay, but it's just not the same, and it's a little different environment, and it's doing different things, and it's responding in a different way.
Right.
And the question is, can it start there? I wouldn't, since we don't know how it started in the first place, nothing surprises me. Okay.
Mm-hmm.
So I think that's the enigma. People, Terry, we all have the kind of like, the world must be pretty much like my hometown here, until,
Right.
I mean, go away to college. Wow, that's interesting. You go away
Right.
to another state, another country.
Right.
It's the same way with planets. We go to Mars and we go, what was its atmosphere like? Must have been one bar, like it is today on the Earth. Why?
Mm-hmm.
Oh, look, it's warm and wet. That must be 273. It's exactly, So there's an anthropocentric,
Yes.
what I call terracentric in a way. We view everything through the lens of course, our own.
Mm-hmm.
And that's something that is pretty dangerous in some ways. Okay, we need to be.
Aliens look like us.
Yeah. Yeah. So anyway, so the key with these missions is that as you move towards getting, as you move towards trying to understand this, you want to explore the surface, you want to explore the minerals, you want to explore the different environments, and to take a look at what's going on and try to figure this out. And is there life there? And what is the environment like? So the last 2 of the Mars Science Labs, okay, that is the laboratory in Gale Crater. Gale Crater is a closed basin lake. We know a water channel flowed in, it had sediments in it, et cetera. So it's exploring that. The Perseverance today is in Jezero Crater. That's an open basin lake. That has a channel flowing in, it has deltas in it. And then the water filled it up and flowed out the other side. Did that happen all at once? Did it happen over multiple times,
Mm-hmm.
or was it a constant background climate? And the key here too in the future is to not just explore these different environments. We have 2 in the case of the last 2 big rovers, the Mars Science Labs, and the Europeans are launching one next year to another similar type of place about the climate. And the Chinese have one operating in Utopia Planitia, which is one of the big basins in the northern lowlands. And what we really want to do is bring samples back, because you can always make more measurements and do much more detailed, sophisticated scientific analysis with samples you bring back. And so that's the goal. In fact, the rover today is, the US rover today is collecting kind of like little chalk stick-like pieces of rock to stow, and we're hoping to go back and get them in a couple of years.
So that's amazing. So the big thing that you just said, I'm going to say it again, is that it might have been that Mars used to be cold and icy. Some event happened that warmed it up. There was this flowing water, and then it went right back to the cold and icy phase. That's something I never knew, but is that the question? Did it happen that way?
Yes.
Or maybe was it it was always warm and wet, and there was only the one transition to cold, or
That's
it
right.
might have gone cold to hot to cold. We're not sure. Okay.
Exactly. Yeah.
That's fascinating.
Yeah. And I'm not convinced either way. I know it's very hard to get the ambient, continuous warm and wet climate. But we've done some climate modeling on that too. What is that like? And then we compare it to where the features are and what they look like, et cetera. It's a big, I would say, I'm trying to test what's called the cold and icy model, which is not the warm and wet one, but the cold and icy one, to see. And we found evidence. One of my students and I just published a couple papers that found really good evidence for glaciation in the highlands. Okay, so is that just like Mount Kilimanjaro glaciation, even though it's on the equator, or is it really indicating a cold and icy Mars? So these are the challenges, and lots of exciting research. And I think the thing that even if conditions were such for the formation of life, only for a short period of time, life is like absolutely incredible. I mean, you look at it in Antarctica, and the mean annual temperature in Antarctica is 20 degrees C below the melting temperature. Okay, that's the average. Okay,
right.
But for a couple of days a year, the daytime peak temperature gets above freezing, and that's when we can thaw the beer out. Okay, and only on very special days. And so the key point there is that we see what happens there. The water, the snow and ice melt from the top. It comes rolling down little streams, and algae is sitting there waiting. And within hours after the water hits that, it actually springs to life. It's just amazing. Okay.
Right.
And then at the end of that season, when the water goes away, it freezes, it dries up and contracts, you know what I mean, drying up and whatever. Yeah.
Right.
And then the wind comes in, blows that stuff all over the place. So it's life waiting for water. So it has a survival mechanism of the way it operates, and then it spreads around by having the wind in the winter spread it around, and then next time water comes in the right place, poop, up it comes. So I would say that if life ever formed on Mars, it's in the subsurface. Conditions on the surface aren't very good, but it's why humans are a marginal species. Bacteria rule the planet. In the time we've had this discussion, there's several generations of bacteria. They're reproducing like crazy. They're going into new little niches and so on. And that's exactly what something would do on Mars. It'd go into the subsurface where it's warmer and it's wetter. So I'm not one of these people who say, oh, it can't be that because it wouldn't be any life. No, I have a great respect for life.
And it's not always just little green men. So you talked about subsurface. This is really interesting. I want to talk about the probes we've sent. Some of them are landers, they're stationary, and some of them are rovers. So can you, like, what landers have we sent and what rovers do we have there? Have we sent?
Yeah, so we sent essentially the two Viking Landers were really important. Viking 1 and 2 in 1976. And
do they still work, by the way? Are they still operational? No. Okay.
But they were great. I mean, they were absolutely great. That was my first planetary mission after Apollo. It was just amazing. I remember sitting at the screen, watching the first lander image come down with Carl Sagan. And Carl is amazing. I mean, like, just of course, so I'm sitting there, Carl, look at the rock, look at the pits in that rock. Maybe that's volcanic. And he sits back in his chair and he goes, Jim, we have just confirmed one of the findings of Paleolithic man. Mars is red. Go, oh my God, how cosmic. I mean, here I'm thinking about little pits and rocks. He's going, it's red, Jim. We've just. But anyway,
I had a picture. My stepdad he built instruments that went on missions to all the planets from Mercury out to Pluto. Cool. And he had an instrument on Viking. So he brought home this panoramic. You probably had it. It was really wide and really narrow from the panoramic camera picture of Mars. I had that in my room as a kid. It was cool.
Those are inspirational, really. So anyway, and indeed, But you couldn't get over the hill. Okay, that's part of the problem. So the rovers became the thing to do, and there was a little Pathfinder rover sometime in the last millennium.
96 or 97, I think, and it landed in a ball. It was a bouncing ball. Is how it got down.
That was a horror story when you watch the simulations there. But it worked. And then the next two did also that, which were the Mars exploration rovers. Those were great too. And the key with that is we could land in different places, and then we could get on the road and rove and see what was behind the next rock and what the local diversity was. At the same time, the resolution of the surface, that is the smallest piece of thing you could see, or like a rock or a hill or something like that, was becoming better and better. And that's a spatial resolution. And the spectral resolution, the wavelength range over which you could actually view the surface, was also really increasing. So, along that time, the Russians and the US and other countries were sending orbiters, which were getting really good data. And, French experiment, Jean-Pierre Bebering was able to talk about the alteration products like the clays and the sulfates and other types of modification that helped us piece together the climate history. And then the climate modelers were studying they're studying the atmosphere with these same spacecraft, but also we're doing climate models based on their data, which helped us to understand. So all of these things came together. Each of them was very complementary, and they began to fill in this picture. And then I think the crowning achievement has really been these Mars Scientific Laboratories, which are these huge, absolutely wonderful things. And, they're way past their expiration date, which not the Jezero one, not the most recent one, but they've all performed just absolutely fantastically. I mean,
and what are those called? The MSL. How many have we launched, and what nickname do they have? Do you remember?
The last one is the ongoing rover today.
Perseverance. All right.
Perseverance is the one, and that's operating in Jezero Crater. And the previous one was in Gale Crater, which is the closed basin lake.
But that was fixed. It was not a rover. It was a lander.
It was a rover. It was just they're both they're very similar to each other. Yeah.
Okay.
So,
and these are big things, right? These are like the size of a golf cart, or they're pretty big.
The size of a golf cart. You just be amazed when you stand next to them. And the Chinese rover is, kudos to them. They got it right the first time. The first attempt at landing.
Yeah.
Yeah, and the data are really incredible. I'm working with them on some of that. It's really fascinating, exciting stuff.
We've had a few failures too, right? We had the Mars Polar Impactor.
Yeah, that was
in '99.
Two of those, and that was that was a really good attempt. Again, we're not going down to the corner store here, okay? So what does the Mars Polar ice deposits and related deposits look like? Well, we don't actually know, but here's what we know, and we try it, and they probably just disappeared into more frothy ice, if you will, or even maybe the ice was too hard, and they impacted. So they were kind of penetrators. But the thing with penetrators is you have to stop close enough to the surface to be able to transmit back.
Well, that was the one. I mean, we got English and SI units.
That was another one. Don't even remind me.
That was a different one.
Can we not talk about that one? Right.
That's okay. Well, I say that. Look, these are the smartest people on Earth, and it's hard to land on Mars. And so when you have failures like that, it makes the successes even more sweet. We're going to have more failures on Mars. I mean, there's going to be we're going to launch other spaceships that don't work, and that's just part of the deal. Then we'll build another one and we'll launch it again. But the Russians have had a really hard time, right? They've had a lot of spaceships crash on Mars.
Yeah, they're on Mars, and so the big test will be Luna 25, which will be launching this summer. Okay. The Luna 24 was a sample return mission in 1976, I think. And a really good mission, absolutely. But they really haven't launched a successful lander since that time.
Since the 70s, yeah.
And they've had,
again, they're smart people. They build good. I flew to space in their space hardware, and it just shows how hard this really is. And so NASA is often a victim of its own success, right?
Well,
The public expects everything's going to work. Like Webb so far has been working, and that there's like 1,000 things that have had to go right so far, and they've all gone right.
yeah,
And it's hard. I like to make that point.
I think you should, because it is not going to the corner store, as we say. And,
Right.
And I think, Dave Scott, when he came back, said to me, he said, the problem with Apollo, Jim, was that we made it look too easy.
Right.
And this is we'll just go on to Mars. Dave has this great slide he made up, which shows the difficulty, sort of like airplanes to orbit to the moon and then to Mars. It's like the magnitude more difficult, but people don't understand the added complexity, et cetera. Just, oh yeah, we go all the time. Yeah, I've seen it on the movies,
Right. Well, so we had Spirit and Opportunity. I think they're both not working now. Is that right?
That's correct. Yeah, they had great lifetimes. I mean,
Oh yeah, it was supposed to be 90 days, and they lasted like a decade or more. And then what was the rover after that? It was there was another rover like in around 2010 or 2012.
Yeah, that's the one I can't remember the name of. And Gale created Perseverance.
And then
Curiosity. No, that's the other one. I can't.
Curiosity. Yeah, Curiosity was back in 2010.
Yeah.
And then we had and Perseverance is the most recent one. So there's several. I think Curiosity is still working. Is that right?
Yep. Mm-hmm. And the thing is here that we'll have another one from Europe being launched this coming year, next opportunity. Right. And or is it this year? Anyway, and then the Chinese one that's operating on the surface.
There's a Chinese, and the missions to Mars. There's like a season. It's like hunting season, and it's every 26 months, right?
Right. It's a kind of like a 2-year launch window, and this is interesting for human exploration because it also dictates when you can come back. Okay. And so, I remember the early days of when we were discussing human exploration of Mars in the late 1980s and 90s. The engineers came and said, look, we need to make a decision here. Do you want to go for just the 45-day window? You get there, you do your stuff, come back, or do you want to wait for 2 years, until you can go?
Yeah.
So what's the question? I mean, why rush?
Right.
We want to go for 2 years. Yeah, of course. That's
so, my perspective is I prefer the spend a month on the surface and come back just because of the radiation.
Yeah, no, you're right.
That is a lot of radiation. And it's a lot in the expense. I mean, launching things to the space station is tens of thousands of dollars a pound. Mm-hmm. Launching things to the moon is hundreds of thousands of dollars a pound. And to Mars, it's probably going to be $1 million a pound, right? So for every one of these on the ISS, I don't know, you can't really see my Diet Coke, but that's tens of thousands of dollars on the ISS, but it may be $1 million on Mars. So there's a lot of reasons to minimize it. Plus, right now NASA's big rocket is called SLS, and the plans are maybe to launch that thing once per year. But a 3-year mission to Mars would take 7 or 9 SLS launches to build the giant Mars ship. So anyway, I'm a fan of the shorter missions personally, until we can get the radiation under control and the cost.
No, I agree with you. But I think the factor in my mind is that it also takes, as you know, from coming back from the ISS, it takes you time to adjust and adapt. You're not going to jump out of the lunar module like Neil Armstrong did and run around the surface and for a couple of hours, and because you're going to have to acclimate to the 1/6 gravity, and 1/3 gravity, and just your body after being in the spacecraft for quite a while.
For the same amount of time, I was on the ISS. I think that would be an interesting mission, would be to launch someone on a 6-month mission to the ISS, bring them back to Earth, and don't help them, and let them do work for some period of time, and then launch them on another mission to the ISS. And that would be a real Mars analog in many ways.
And you turn them over to the geologists when they touch down. You know what I mean?
Right.
It's just like, okay, here's your hammer. Let's go. We're going.
Exactly.
That's a really good idea.
Bring them out to Arizona. So what, if you could design the Mars mission, what would it be? If it was going to be the Dr. James Head Rover, what instruments would it have? What craters would it go to?
Yeah, I think first of all, it would have a couple of my grad students driving it. Okay, that's the first thing. Not for me, but because that's they're the ones that need to go. And so I think human exploration of Mars would be absolutely fantastic. I mean, absolutely fantastic. Short of that, I would say, I think the capabilities we have on these rovers are really, really astonishing. And I think we're on the right track with Jezero. We actually did a lot of research work on that. And, when you select these landing sites, when NASA does, they have kind of like a bake-off, okay?
Right.
All the scientists get together and they present their, oh, look at my donuts, look at my cake here, and we were in the top 5, and then we finally, ours was the favorite site, which is great. I mean, the grad students did an absolutely incredible job.
Wow. So you helped pick, or you picked the last landing site.
But NASA picks the landing sites, okay?
Right, but it was your site that got picked.
That's right. Tim Gouge and Caleb Fassett and many other of the students at Brown really were the people.
Wow, that's awesome.
Yeah, we did.
Congrats.
The group at Brown did a lot of work on that. It's great. It's very exciting. So I think that's an example of what we would want to know, and I think. There's so many other mysteries, and my idea here is to not so much just to have one, but obviously do the multiple types of things. I think exploring some of the glaciated terrains would also be absolutely fantastic. And we have these things, these sulfates in the bottom of this huge valley, Valles Marineris, and nobody understands how the hell they form. And so that's another one. We're going to the top of some of these volcanoes and really looking at the mineralogy of the rocks, the characteristics of them, et cetera. And we really need more sample return. That's absolutely critical because of the ages, the composition and so on. There's just so many different areas. It's really hard to tune in on one, but we did on this one, and it's a question of priorities and what the next step is. The other thing is you learn so much from each mission. It's like Apollo. We would debrief the crews, analyze the samples, and we factor that back into the next landing site for crying out loud, which 3 or 4 months later.
Right. That's amazing.
Yeah.
That's the kind of feedback loop that you need in your decision making. In the military, we called it the same thing for picking targets, but you're on Mars, you're picking targets also. Yeah. I don't know if I told you this. When we were in space on Expedition 43, a good friend of mine, Dr. Jim Rice, was out at ASU. So a big part of, Jim.
Oh
yeah. A lot of guys know. So he's a big Mars guy. And so I got to fly out to JPL, and when they found the blueberries, the proof of water on Mars. And I went to ASU with John Young. Actually, I flew with him in a T-38. And so I'm in space, and he sent me up this package of materials, and me and Samantha and Anton, we sat around a laptop and we picked out a rock. And then they sent the rover over, and it sampled the rock that we picked out. So that was really cool. I did some
that is really cool.
Astronaut remote geology on Mars from the ISS. It was really cool.
That's cool. Yeah, that's really great.
And I told our NASA public affairs guys, I said, hey, I'm doing science on Mars from the ISS. You guys might want to tweet about this or something. And they said, no, they had another public affairs campaign that they were doing at the time, and so no, we're doing this other thing now, we're not going to tweet about that. So I'm like, whatever.
Yeah, Jim Rice is a really, he spent he's a not only a Planetary and Mars colleague of mine, but he also spent time in Antarctica. He spent a season in Antarctic in the Russian base
with the Russians scuba diving. I know.
God,
NASA should have picked him. He interviewed with me to be an astronaut, and they should have picked him. He would have been a great astronaut, but has done great work. Yeah, I'm going to have him on the podcast too. We'll talk about some more Mars stuff. So you're focused on the human exploration. So here's a question that's really important, and that's planetary protection, because wherever people are, they're breathing germs and bugs, and and then if we leave some bugs there, and then the next rover comes along and they go, oh, look, we found more life on Mars. And so how big of a threat is that? Should we worry about it? What if we germinate life on Mars and the planet becomes inhabited in the next 1,000 years because of the germs we leave behind?
Well, it's a very, very big problem. I mean, I think is brought even more to the fore by COVID, where you realize how contagious something can be. I mean, like planetary scale. And,
Mars will have to be in a lockdown.
Well,
We bring COVID there.
Exactly. And I think, that's why, yeah, I mean, coming back from the ISS, uh, Jessica Meir, one of my ex-students, she came back in the middle of the whole thing. It's like, whoa, what's that?
Yeah.
Tough. But anyway, here's the first thing I think everybody needs to understand is that the first human that sets foot on Mars is essentially a walking Noah's Ark of microbes. There is no way you're going to avoid contamination. When we go to Antarctica, the credo is leave footprints only, leave only footprints and try not to leave those. But you can't, we always make sure we don't have any, soil or anything on our clothes when we're leaving or going back, et cetera, vice versa.
Right.
But it just you can't avoid it. Humans just exude billions of microbes, and I think that has to be really, really carefully thought out. And I think there's no way we can do anything other than moderate. We can't avoid contamination. We can't be wearing hazmat suits the whole time because they still emit.
Right. Well, and you're not going to bring all that waste back. You're going to leave waste on the surface. You're not going to ship a can of poop from Mars back to Earth, right? So when you go to Everest, or I did some training with an organization called Knowles, and the philosophy is leave no trace. And so you actually bring the can of poop back with you, right, when you go camping. But when you go to Mars, we're going to have to leave stuff behind. So it's just, it is what it is. Either we don't ever send humans away from Earth, or we just accept that is going to happen. And maybe there's nothing wrong with that. Maybe that's just part of the way the universe is. If you explore, you leave some trace behind. You try and minimize it. Maybe you leave it out where it's exposed. You don't want to protect it from radiation. You leave it out in the radiation. So most microbes would be killed by the radiation.
Those are the kind of things one needs to be exploring over the course. Yeah.
Right.
Yeah.
That I hadn't really thought of it until you just were talking about the humans, and I'm like, we're going to leave.
We're Noah's Ark. Noah's Ark. I mean, get that in your head.
Right.
Noah's Ark. I mean, we may not share some, but we share billions of microbes. You know what I mean?
Right. Not only human. I mean, any life. If you had a dog there, or there's, as long as there's life from Earth. And I think back in the 60s, they found that there was a probe that had gone to the moon, and Apollo 12 landed next to it. Yeah. And they found there were still microbes on it or something like that.
Yeah, that was the finding at the time, that it was in the cables, that had gone to the moon, stayed there for several years, brought back, and it had them in there. There's an issue about contamination. I don't know the details of that, but some people think it might have gotten contaminated during put into the receiving lab, et cetera.
During the return, right? Okay. Well, anyway, it's an interesting thing.
Yeah, be a good experiment.
Well, Mars is the place to be. Every time I did a speech with some middle schoolers today, and they asked me about how we get to Mars. It's something that we need to get there. Mars has been 20 years in the future ever since Werner von Braun landed us on the moon. In 1969, they asked him, and he said, we'll be there by 1989. And then in 1989, you alluded to the Space Exploration Initiative, that George H.W. Bush was going to send us to Mars. And then the Admiral Truly, I think the NASA administrator, brought a multi-$100 billion price tag, and he was like, maybe not. Yeah. So we've been 20 years from Mars for a long time. We'll see if maybe the new private space companies can get there quicker.
Well, my money's with SpaceX. I think, I do some work with them, and they're really obviously looking for the most important resources, which is water. Okay. And, there's a lot of water in the equatorial regions that is not far below the surface. We've mapped all that out, and we know where it is. So we're working with them on, okay, what do you do to get that? How, and what kind of support do you need, and so on. And that's where my money would be.
You can see water in the polar ice cap. I used to have a little 5-inch refractor telescope, and in the right season, you could see the polar ice caps. And a lot of that's carbon dioxide ice, but there's also water ice in the poles. But it's also minus 100 degrees or whatever. It's super cold there.
It's super cold, and it actually is mostly water ice. People have
Hmm.
where every 6 months or maybe 3 months we said water on Mars. Whoa, we've known that for a long time.
Been there for a billion years. Yeah.
Yeah, and we also know that it has to be mostly water ice because if it was CO2 ice, um, CO2 ice is more like Cairo or like maple syrup than it is like a rock. Okay.
Oh, I didn't know that.
Yeah. So you actually, if those polar caps were CO2, they'd be they just flow away. But
Huh.
there is some CO2. We know that from the remote detections, and we also see little pits that form that are very symptomatic of that. And that's a big deal, going back and forth in the atmosphere. But in general, they're mostly water ice. That's the major resource, near surface resource. If you melted all that down, it would be about 20 or 30 meters over the whole planet, for example.
Wow.
Layer thick.
If there was global warming on Mars, it would have a 20 or 30 meter ocean. That's incredible. That's a lot of water.
Yeah, it would be even more because that's an average layer. We call it the GE,
right.
the global equivalent layer of water.
Wow.
So it would be that much. And that's a big argument. People have discussed the possibility of oceans on Mars in the past, and I think they see a lot of evidence, and we're testing as well. So yeah,
testing that hypothesis. But there's even water in the equatorial regions. I did not realize that. But then you have to dig it, and that's not easy to get.
Well, it's good news and bad news. The fact that you have to dig it means that it's protected. Otherwise, it would sublime away.
Right.
And the bad news is, what's the depth? Okay, so we see some debris-covered glaciers that have hundreds of meters of ice in their interiors, and we can see them with a charade data, which is a radar penetrator that can actually see through the ground, and we see the ice underneath there. And then there's flat areas which have a few meters, tens of meters of ice that has flowed out and then frozen and then covered with dust. So imagine dirty water flowing out onto the surface. Some of the ice sublimes away. It just evaporates away, and it concentrates soil layers or dust layers on top, and that protects it from further loss. So there's lots of evidence for water ice in various parts of the near equatorial regions, which is what we're trying to look at with SpaceX, for example.
Very interesting. Well, there's a lot of cool things to do on Mars. And when I talk to these kids, hopefully they can go there in the not too distant future. SpaceX, I've had Eric Berger on, and he's a space reporter several times, and he wrote a book about SpaceX, and there's good and bad about everybody, but they have really done amazing things really quickly. They got a contract from NASA, a basic contract in 2005. I think the real COTS contract was in 2008. And 4 years later, in 2012, they were delivering supplies to the space station. Yeah. I mean, in just a handful of years.
Yeah. I've been on the, we talked about this before, I think, but I've been on the floor at Hawthorne of the SpaceX place.
Their facility.
And it's most like being an Apollo that I've seen since that time. It's like the young people, energetic, totally dedicated, very good, and they're on a mission.
Yeah.
Okay. And it's I have great respect for them. I just got Ann gave me Eric Berger's book for Christmas, so I'm going to take a look at it myself. See.
Eric's a great. I think he's the best space reporter out there. He's really good. But to put it in context, basically SpaceX got a grant in 2005. They got a contract in 2008. Since then, they've built the Falcon 9 rocket. It's launched hundreds of times. It's the one that comes back and lands. The first stage comes back and lands. They've delivered cargo to the ISS. That rocket has completely disrupted the global launch industry. It's basically ended the Russian commercial launch program because SpaceX does it better and cheaper. They've made human spaceships that we go up into space. They built the Falcon Heavy. That's a pretty big rocket. And they've started developing their Starship, which is the BFR or whatever. It's a really big rocket. They haven't launched that yet into orbit, but they've done test flights with it and so on. And so that's what they've done since 2005.
Yeah.
NASA had the Constellation program was born in 2005, and part of that was Ares 5, this big giant rocket. Right. And they changed the name to SLS, but it's the big rocket that was born in 2005. And it hasn't flown once. So from the same starting point, and it's had a budget of, we're spending several $billions a year on it. Mm-hmm. We also started the Orion capsule, and it was born in 2000. All these things were born at the same time, and it flew once. It flew unmanned on a Delta rocket when I was in space. We actually watched the launch from the ISS. So if you look at those three programs, SpaceX, Orion, and SLS, the same starting point. Orion has about $1 billion a year budget. SLS has a couple $1 billion a year, and it's striking the different level of progress in all of those and level of cost. Anyway, I'll just say that out loud.
Yeah, no, I think, and yeah, I mean, there's a lot of residual hardware that is residual, what I call residual political hardware, which was part of that program and got retained for reasons about, capabilities in certain congressional districts. And I think that's not a good way to manage a space program, personally.
Well, you can see, it's not what I think. It's these are the facts. I just laid out how it happened. Well, anyway, I think that's a good place to wrap up today's podcast on Mars. I still want to talk about the outer planets and especially the moons. I think the moons are the coolest part about that. Europa and Enceladus, maybe there's some places where there might be life, and maybe we can continue these lessons we've been getting.
Yeah, it would be great. And I have a student, Erica Nathan, who has just finished a synthesis of the icy outer planet moons. So she has a lot to say too. Maybe it'd be fun to bring her along for a part of it.
If she wants to do it, I would love. Let's. If she's willing, please invite her. I would love.
She's great.
So she could do the icy moons.
Yeah, we could have a conversation together. I've got the history of that. I was on the Galileo mission and all the other,
right.
And she's got the total excitement about where things are, Pluto, how that fits into the Kuiper Belt objects and all these other things that so that'd be
KBO.
Great.
Let's do it next. Okay.
All
right. Well, thanks. And once again, I'll say, if you love the podcast, please don't forget to subscribe and give us a rating. So we'll see you next week.